Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The sky has always been humanity's greatest theater, displaying spectacular performances that could bring life or devastation. Long before satellites and weather stations, ancient civilizations gazed upward, desperate to decode the atmospheric mysteries that governed their survival. In ancient Babylon, around 1500 BC, priest astronomers meticulously recorded weather patterns on cuneiform tablets. They noticed correlations between celestial movements and seasonal changes, creating the first systematic weather observations. These early meteorologists understood that atmospheric phenomena followed patterns even if they couldn't explain the underlying physics. The ancient Greeks elevated weather study from mere observation to philosophical inquiry. Aristotle, writing around 350 BC, authored Meteorologica, the first comprehensive treatise on atmospheric science. He correctly theorized that water evaporated from oceans to form clouds, though he mistakenly believed earthquakes caused wind. His work dominated meteorological thinking for nearly 2,000 years, demonstrating both the power and limitations of early scientific reasoning. Chinese scholars during the Han Dynasty, around 200 BC, developed sophisticated instruments for atmospheric measurement. They created the first hygrometers, using stretched silk to measure humidity, and invented weather vanes to determine wind direction. Their detailed records of storms, droughts, and unusual atmospheric phenomena provided invaluable data that modern climatologists still reference today. Medieval Islamic scholars preserved and expanded upon Greek meteorological knowledge. Al-Kindi in the 9th century wrote extensively about atmospheric optics, explaining why the sky appears blue and how rainbows form. Ibn al-Haytham advanced the understanding of atmospheric refraction, laying groundwork for later discoveries about how light behaves in our atmosphere. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The Renaissance brought revolutionary changes to atmospheric science. Leonardo da Vinci conducted the first systematic studies of cloud formation, creating detailed sketches of different cloud types and theorizing about their formation mechanisms. He observed that mountains affected local weather patterns, laying early foundations for topographic meteorology. In 1593, Galileo Galilei invented the thermoscope, the predecessor to the modern thermometer. For the first time, humans could quantify temperature changes, transforming weather observation from qualitative descriptions to quantitative measurements. This innovation marked the beginning of modern atmospheric science, where precise measurement became the foundation of understanding. Evangelista Torricelli's invention of the barometer in 1643 provided another crucial tool. By measuring atmospheric pressure, scientists could finally begin to understand the relationship between pressure changes and weather patterns. Torricelli's discovery that air had weight revolutionized thinking about the atmosphere as a physical entity with measurable properties. Robert Hooke, in 1664, created the first mechanical weather station, automatically recording temperature, humidity, and wind direction. His systematic approach to data collection established protocols that modern meteorologists still follow. Hooke recognized that understanding weather required continuous monitoring rather than sporadic observations. By 1700, European scientists had established weather observation networks across multiple countries. They shared data through correspondence, creating the first international cooperation in meteorological research. These early networks revealed that weather systems moved across continents, challenging the prevailing belief that weather was purely local phenomenon. The foundation stones of atmospheric science were set by these early pioneers who combined careful observation with ingenious instrumentation. Their work transformed weather from divine mystery to natural phenomenon, establishing the scientific framework that would eventually allow humanity to predict and understand the complex atmospheric processes that govern our planet's climate system. The 18th century ushered in an era of precision that transformed atmospheric science from philosophical speculation into rigorous scientific discipline. Revolutionary instruments and systematic observation networks emerged, laying the foundation for modern meteorology and revealing the atmosphere's true complexity. Benjamin Franklin's groundbreaking electrical experiments in the 1750s fundamentally changed understanding of atmospheric electricity. His famous kite experiment in 1752 proved that lightning was electrical in nature, not divine punishment. Franklin's work led to the invention of lightning rods and established the first scientific explanation for thunderstorm formation. He also discovered that storms moved from southwest to northeast across North America, contradicting the prevailing belief that weather moved with prevailing surface winds. The invention of more precise instruments accelerated atmospheric research. Daniel Gabriel Fahrenheit developed the mercury thermometer in 1714, providing accurate temperature measurements. Anders Celsius created his temperature scale in 1742, while René-Antoine Ferchot de Réaumur introduced another temperature scale. These standardized measurement systems allowed scientists worldwide to compare observations meaningfully. Luke Howard revolutionized cloud classification in 1803 with his systematic nomenclature. He identified 4 basic cloud types: cumulus, stratus, cirrus, and nimbus. Howard's classification system, still used today, provided meteorologists with a common language for describing atmospheric conditions. His work demonstrated that clouds followed predictable formation patterns based on atmospheric temperature and humidity profiles. The establishment of national weather services marked a crucial turning point. In 1870, the United States created the Weather Bureau under the Signal Service Corps. This organization began issuing the first systematic weather forecasts, using telegraph networks to rapidly share observations across vast distances. The telegraph revolution enabled meteorologists to track storm systems in real time, transforming weather prediction from local guesswork to continental-scale science. Admiral Robert Fitzroy, former captain of Charles Darwin's Beagle voyage, became Britain's first official weather forecaster in 1854. Fitzroy coined the term weather forecast and established the first storm warning system for shipping. His daily weather maps, published in the Times newspaper, introduced the general public to systematic weather analysis. Fitzroy's work saved countless lives by providing early warnings of dangerous storms approaching British coastal waters. The invention of weather maps revolutionized meteorological visualization. Heinrich Wilhelm Brandes created the first comprehensive weather map in 1820, plotting conditions across Europe for a specific date. These maps revealed that weather systems had coherent structure across hundreds of miles, challenging the notion that weather was purely random. Meteorologists began recognizing patterns: areas of low pressure associated with storms, high pressure associated with clear weather. Systematic balloon observations began in the late 19th century, providing the first direct measurements of upper atmospheric conditions. Léon Tisserand de Bort's balloon experiments in the 1890s discovered the stratosphere, revealing that Earth's atmosphere had distinct layers with different temperature profiles. This discovery fundamentally altered understanding of atmospheric structure and circulation patterns. The development of international cooperation accelerated meteorological progress. The first International Meteorological Congress in 1873 established standardized observation protocols and measurement units. Countries agreed to share weather data freely, recognizing that atmospheric phenomena crossed political boundaries. This cooperation laid the groundwork for modern global weather monitoring systems. William Ferrel's theoretical work in the 1850s provided the first mathematical description of atmospheric circulation. Ferrel's law explained how Earth's rotation deflects moving air masses, creating the characteristic wind patterns that drive global weather systems. His work bridged the gap between observational meteorology and theoretical atmospheric physics. By 1900, meteorology had evolved from ancient sky watching to a sophisticated science combining systematic observation, precise instrumentation, and mathematical analysis. Weather services operated across multiple continents. Storm warning systems protected maritime commerce, and theoretical frameworks explained atmospheric behavior. The stage was set for the 20th century's revolutionary advances in atmospheric understanding, which would transform weather prediction from educated guesswork into precise science. The early 20th century witnessed a scientific revolution that transformed meteorology from descriptive observation into predictive mathematical science. Pioneering researchers unlocked the fundamental physics governing atmospheric behavior, revealing the complex dynamics that drive weather systems across our planet. Wilhelm Bjerknes, the Norwegian physicist, established the theoretical foundation of modern meteorology in 1904. His groundbreaking work applied principles of fluid dynamics and thermodynamics to atmospheric motion, creating the first mathematical framework for weather prediction. Bjerknes demonstrated that atmospheric behavior followed physical laws, making weather forecasting theoretically possible through mathematical calculation rather than empirical guesswork. The Bergen School of Meteorology, founded by Bjerknes and his colleagues after World War I, revolutionized understanding of storm formation. Jacob Bjerknes, Wilhelm's son, discovered the polar front theory in 1919, explaining how cold Arctic air masses collide with warm tropical air to create cyclonic storms. This breakthrough revealed that weather systems had predictable life cycles developing along boundaries between different air masses with characteristic temperature and humidity profiles. Tor Bergeron's research in the 1920s uncovered the microphysics of precipitation formation. The Bergeron-Findeisen process explained how ice crystals grow in supercooled clouds, eventually becoming raindrops or snowflakes. This discovery connected cloud-scale physics to large-scale weather patterns, demonstrating how microscopic processes influence continental-scale atmospheric phenomena. The discovery of jet streams represented another major breakthrough. Japanese meteorologist Wasaburo Oishi first observed these high-altitude wind currents in the 1920s using balloons, but his work remained unknown outside Japan. During World War II, Allied bomber crews flying over the Pacific encountered mysterious headwinds exceeding 200 miles per hour. These observations led to the recognition of jet streams as rivers of fast-moving air in the upper troposphere, fundamentally altering understanding of global atmospheric circulation. Carl Gustav Rossby's research in the 1930s and 40s provided crucial insights into large-scale atmospheric dynamics. Rossby waves, the massive undulations in the jet stream, explained how energy propagates through the atmosphere and influences weather patterns across entire continents. His work demonstrated that local weather events were connected to planetary-scale atmospheric motions, establishing the foundation for modern weather prediction systems. Lewis Fry Richardson attempted the first numerical weather prediction in 1922, manually calculating atmospheric changes using mathematical equations. His heroic effort required 6 weeks of calculations to produce a 6-hour forecast, which proved wildly inaccurate due to computational limitations and insufficient initial data. Despite the failure, Richardson's work established the theoretical framework for numerical weather modeling that would later revolutionize meteorology. The role of Earth's rotation in atmospheric dynamics became increasingly clear through the work of William Ferrel and later researchers. The Coriolis effect, caused by Earth's rotation, deflects moving air masses and creates the characteristic spiral patterns of cyclones and anticyclones. This understanding explained why storms rotate clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, providing crucial insights into storm structure and movement. Upper air observations expanded dramatically during the 1930s with the widespread adoption of radiosondes, instrument packages carried aloft by weather balloons. These devices transmitted real-time measurements of temperature, humidity, and pressure at various altitudes, revealing the three-dimensional structure of atmospheric phenomena. Radiosonde data exposed the complex vertical structure of weather systems, showing how conditions at different altitudes influenced surface weather patterns. Advances in atmospheric optics and radiation physics illuminated how solar energy drives weather systems. Scientists discovered that differential heating between poles and equator creates the fundamental energy imbalances that power atmospheric circulation. Understanding of how clouds, water vapor, and atmospheric gases absorb and reflect solar radiation provided insights into the energy budget governing Earth's climate system. By 1950, meteorologists possessed a comprehensive theoretical framework explaining atmospheric behavior from molecular to planetary scales. The stage was set for the computer revolution that would transform weather prediction from an art based on experience and intuition into a precise science based on mathematical modeling and massive computational power. The 1950s marked the beginning of meteorology's digital revolution, as electronic computers transformed weather prediction from educated guesswork into precise mathematical science. This technological transformation, combined with space-based observations, fundamentally altered humanity's ability to understand and predict atmospheric behavior. John von Neumann, the brilliant mathematician and computer pioneer, recognized that weather prediction was perfectly suited for electronic computation. In 1950, his team at the Institute for Advanced Study produced the first successful numerical weather forecast using the ENIAC computer. Their 24-hour prediction, calculated in 24 hours of continuous computing, demonstrated that mathematical models could capture atmospheric behavior with unprecedented accuracy. The development of more sophisticated computer models accelerated rapidly throughout the 1950s and 60s. Norman Phillips created the first general circulation model in 1956, simulating global atmospheric circulation patterns. These early models, though crude by modern standards, successfully reproduced major features of Earth's weather systems, including the formation of storm systems and the behavior of jet streams. Weather radar technology, developed during World War II, revolutionized storm observation and tracking. The 1950s saw the deployment of weather radar networks across the United States and Europe, providing real-time views of precipitation patterns and storm intensity. Doppler radar, introduced in the 1970s, added the ability to measure wind speeds within storms, dramatically improving tornado and severe weather prediction capabilities. The launch of TIROS-1 in 1960 initiated the satellite age of meteorology. This television infrared observation satellite provided the first space-based weather images, revealing cloud patterns and storm systems across entire continents. Meteorologists could finally observe weather development in remote ocean areas, filling crucial gaps in global weather monitoring networks. Geostationary weather satellites, beginning with ATS-1 in 1966, provided continuous monitoring of weather systems from fixed positions above Earth's equator. These satellites revolutionized hurricane tracking, allowing meteorologists to observe storm formation and intensification over tropical oceans. The ability to monitor cloud patterns continuously transformed understanding of storm life cycles and improved hurricane landfall predictions. The 1970s brought increasingly sophisticated satellite instruments measuring atmospheric temperature, humidity, and wind patterns at multiple altitudes. These observations provided the comprehensive three-dimensional data needed for accurate numerical weather models. Satellite sounders could measure atmospheric profiles in areas completely lacking ground-based observations, particularly over oceans and polar regions. Numerical weather prediction models became increasingly sophisticated throughout the 1970s and 80s. The development of primitive equations models, which solved the fundamental mathematical equations governing atmospheric motion, provided more accurate forecasts than earlier simplified approaches. These models incorporated complex physics, including radiation transfer, cloud formation, and surface energy exchange. The emergence of ensemble forecasting in the 1990s addressed the inherent uncertainty in weather prediction. Rather than producing single forecasts, meteorologists began running multiple model simulations with slightly different initial conditions. These ensemble forecasts provided probability estimates for different weather outcomes, acknowledging the chaotic nature of atmospheric systems while providing useful uncertainty information. Supercomputers became essential tools for weather prediction, as models incorporated increasingly detailed physics and finer spatial resolution. The Cray-1 supercomputer, installed at the National Center for Atmospheric Research in 1976, enabled weather models with unprecedented detail and accuracy. Computing power doubled regularly, allowing models to simulate atmospheric processes at progressively smaller scales. Advanced satellite systems, like the Advanced Very High Resolution Radiometer, provided detailed measurements of sea surface temperatures, vegetation patterns, and atmospheric composition. These observations revealed connections between ocean temperature variations and weather patterns, leading to improved understanding of phenomena like El Niño and La Niña and their global climate impacts. By the 1990s, numerical weather prediction had achieved remarkable accuracy. 5-day forecasts had become as accurate as 3-day forecasts were in the 1970s. Hurricane track predictions improved dramatically, with forecast errors decreasing by approximately 50% per decade. The combination of satellite observations, sophisticated computer models, and powerful supercomputers transformed meteorology into one of the most successful predictive sciences. The computer revolution established the foundation for modern weather prediction systems that protect lives and property worldwide, setting the stage for 21st century advances in climate modeling and atmospheric understanding. The 21st century has ushered in an unprecedented era of atmospheric understanding, where climate science, artificial intelligence, and revolutionary observation technologies converge to unlock previously hidden secrets of our planet's weather systems and long-term climate behavior. Climate modeling has evolved far beyond simple weather prediction to encompass Earth's entire climate system. Modern Earth system models simulate interactions between atmosphere, oceans, ice sheets, vegetation, and human activities across timescales from days to centuries. These sophisticated models revealed that Earth's climate operates as an integrated system where changes in one component can trigger cascading effects throughout the entire planetary environment. The Coupled Model Intercomparison Project has coordinated climate research globally, enabling scientists to compare model predictions and identify robust climate projections. These collaborative efforts produced the climate assessments underlying international policy decisions, demonstrating how atmospheric science now influences global governance and environmental policy at the highest levels. Extreme weather prediction has achieved remarkable precision through advances in high-resolution modeling and ensemble forecasting techniques. Modern hurricane models can predict storm tracks with errors of less than 100 miles at 5 days, while tornado warning lead times have increased from minutes to hours. The development of storm-scale ensemble forecasting systems provides probability-based warnings that help emergency managers make better decisions about evacuations and resource allocation. Artificial intelligence and machine learning have begun revolutionizing weather prediction and climate analysis. Deep learning algorithms can identify patterns in massive data sets that human analysts might miss, improving precipitation forecasts and extreme weather warnings. AI systems process satellite imagery to detect rapidly developing storms, analyze radar data to improve tornado predictions, and optimize weather model performance by learning from forecast errors. The integration of big data analytics with traditional meteorological approaches has opened new research frontiers. Social media, data, smartphone sensors, and Internet of Things devices provide unprecedented amounts of real-time atmospheric information. Crowdsourced weather observations from personal weather stations, vehicle sensors, and mobile applications supplement traditional observing networks with hyperlocal data coverage. Next-generation satellite systems have revolutionized atmospheric monitoring capabilities. The GOES 16 and 17 satellites provide weather imagery with 16 times better resolution and 5 times faster update rates than previous systems. These advanced sensors can detect rapidly developing thunderstorms, monitor wildfire behavior in real time, and track air quality changes with unprecedented detail. Polar orbiting satellites equipped with advanced sounders provide vertical profiles of atmospheric temperature and moisture, with accuracy approaching ground-based radio sondes. The Joint Polar Satellite System represents a quantum leap in global atmospheric monitoring, providing critical data for both weather prediction and climate monitoring across Earth's entire surface. Phased array radar technology promises to revolutionize severe weather detection and tracking. These electronically steered radars can scan the entire sky in under 1 minute, compared to 5 minutes for conventional rotating radars. This capability enables meteorologists to track rapidly evolving storms with unprecedented temporal resolution, potentially improving tornado warning accuracy and lead times. Climate attribution science has emerged as a crucial discipline, using statistical analysis and climate modeling to determine how human activities influence specific weather events. Scientists can now quantify how greenhouse gas emissions affect the probability and intensity of heat waves, droughts, floods, and storms, providing crucial information for adaptation planning and policy decisions. The development of seamless prediction systems integrating weather and climate forecasting represents a major paradigm shift. These systems provide consistent predictions across timescales from hours to decades, enabling better decision-making for agriculture, water resources, energy systems, and disaster preparedness. Sub-seasonal to seasonal forecasting fills the critical gap between weather and climate predictions. Emerging technologies like quantum computing and advanced AI architectures promise to unlock even greater atmospheric understanding. Quantum computers could solve complex atmospheric equations that are currently computationally intractable, while neuromorphic computing architectures might process environmental data with unprecedented efficiency and speed. The future of atmospheric science lies in increasingly sophisticated integration of observations, models, and artificial intelligence. As Earth's climate continues changing, atmospheric scientists stand at the forefront of humanity's efforts to understand, predict, and adapt to our planet's evolving weather and climate systems. The journey from ancient skywatchers to modern climate scientists represents one of humanity's greatest intellectual achievements, with the most important discoveries yet to come.